All right, guys, welcome to 11.5 part 2, and let's pick up where we left off. So this one I want you to try on your own, but first, the goal is to find the first 5 terms, but before we can do that, we need to find the equation, which is what we were just working on. And just like the previous examples, I gave you 2 points, unfortunately, that are not the first term. So on the 4th term, the output is 16. On the 10th term, the output is 46. What I'd like you to pause and do is find the d value via slope. And once you find d, I would like you to take one of these points, plug them in for a sub n, and find your a sub 1 value, and see if you can find the equation on your own. So please pause, take a look at your previous example, and see how far you can get on your own. So please pause now. All right, guys, so to check in with you, when I found my slope or my common difference, I got 5. So what I did was I plugged 5 in for the common difference and then had to solve for the first term. I picked this point to use. This is my n value and this is my a sub n value. So I did some substitution here and here, and I simplified. 16 equals a sub 1 plus 5 times 3. If I subtracted 15 over, I got that my first term was 1. Which meant in my equation, a sub n equaled the first term of 1 plus the common difference of 5 times n minus 1. Simplified this and got this to be 5n minus 4. Now this might be a good point to pause the video if you would like to write more of this down. But I'm going to keep going. If now I want to find all of these values, we already found that a sub 1 was 1. But if you want to find the second term, you can plug it in here. A sub 2 would be 5 times 2 minus 4, which would be 6. A sub 3, which would be 5 times 3 minus 4. From here, 15 minus 4 is 11. And if you continue to do that, the next term would be 16, and the next term would be 21. So again, the whole point of this is to find this general equation so that you can find these values. Last but not least, from the first section, find the nth term of the following sequence. It gives me the first term, but it looks like the equation it gives me is recursive. And remember, if it gives you a recursive equation, that this number really equals the common difference. So if you want to find the nth term, this one is much better than the previous example. Because if you're trying to find this, do we have a sub 1? Yes. Do we have the common difference? Yes, we do. It's 4. So this is more just plug and chug. The nth term would equal 15 plus 4 times n minus 1. So the nth term would be 15 plus 4n minus 4, or the nth term would be 4n plus 11. So knowing that the recursive sequences, that this is the common difference, saved me a lot of time. So there'll be a lot more practice of stuff like this in class, in the next class period. However, I would like to transition to the second part of these notes, which is over arithmetic sequences, specifically the sum of them. And you might remember that the sum looked like this sigma symbol, and we had 2 types of sums. We had finite sums, and we had infinite sums. And in this video mainly, we're going to be focusing on finite, meaning something like from the first term to the 8th term, because I don't want to be adding on forever and ever. We're going to be focusing on finite here. So this brings me to a mathematician named Gauss, and he's going to help us discover how to quickly find the sum of any arithmetic sequence. So when Gauss was in 3rd or 4th grade, his teacher wrote this problem on the board. He asked his students, I would like you to find the sum of all numbers from 1 to 100. So the goal is to find the sum. Now Gauss's classmates just started saying, okay, 1 plus 2 plus 3, and kept adding and adding and adding. But Gauss suddenly said, I think the answer is 5,050. And his teacher stopped in astonishment and said, how in the world did you get that so quickly? And what Gauss said was he noticed that if he added up the first and the last term, he would get 101. And then if he added up the second and the second to last term, 2 and 99, you would also get 101. And if he added up 3 and 98, you would also get 101. And then he thought to himself, there's 100 numbers. That means there's 50 pairs of sums of 101. So he took 50 pairs times the sum of 101 and get 5,050, which is exactly correct. And so if we think about where that really came from, I mean, that's amazing that he found that. But remember that there is 100 terms at the beginning of the problem. So 50 is really the number of terms divided by 2, and 101 can be written as the first term of 1 plus the last term of 100. So 5,050 can be found this way as well. Let's see another example so we can start to generalize. Find the sum of the numbers from 1 to 1,000 without simply adding them together. So if I took 1 plus 2 plus 3 plus 4, plus 998, 999, 1,000. So this one's even more numbers. So if we think about using Gauss's idea, and we take the first and the last term, that's 1,001. The second and the second to last term is also 1,001. And if there's 1,000 numbers, that means there's 500 pairs. So if we took 500 pairs and multiplied that by 1,001, we would get a total sum of 500,500. And again, if we think about generalizing that eventually, 500 is really the number of terms n divided by 2, and you can split 1,001 into the first term plus the last term of 1,000. So if I started to generalize this idea, the sum of any arithmetic sequence is going to be the nth term divided by 2, and you could think of the nth term in this example as 1,000, times the first term, which we call a sub 1, and the nth term or the ending term, which we call a sub n. And so this formula can help us find the sum quickly. So just to reiterate, this really represents the total number of terms added. A sub 1 represents the value of the first term. A sub n really represents the value of the nth term. And something to point out is that a sub 1, the first term, does not always mean n equals 1. So it does not always mean n equals 1. That could represent any first term in the sum, which we will get to. And this idea of what Gauss had helps us do it much more quickly. So we don't have to do 1 plus 2 plus 3 plus 4. I think some of you would say, Mrs. Logus, seriously? If you had me find the sum from 1 to 1,000 without a quicker way? No, thank you. Let me show you how this formula can be used quickly in the next two examples, so it goes from general to actually useful. So I already wrote the formula on the next page, and your goal is to find the sum from the number 1 to the number 100. And this would take forever without Gauss's formula. And so the number of terms from 1 to 100 is 100 terms. So my sum is going to be 100 terms divided by 2, which we got from Gauss's idea. A sub 1, remember, doesn't represent 1. It represents the first term. So I'm going to find a sub 1. And to find that, you plug 1 into your function. So it's 2 times 3 times 1. So a sub 1 is 5. And a sub n represents the last term you're finding, which is 100. So a sub 100 is 2 plus 3 times 100, which is 300 plus 2, or 302. And so to find the sum, what we would do is do 100 divided by 2, a sub 1 is 5, a sub n is 302. So the sum would be 50, if you reduce, times 307, and 50 times 307 is 15,350. So this would be my sum much more quickly than doing it the long way. The next example is a good one because notice again that we did not start with n equals 1, which is what I mentioned earlier. This just represents your first term. But here we need to be careful. On this example, if we counted from 1 to 100, we did get exactly 100 terms. But this one, if we're going from 5 to 25, you need to be careful. A lot of you might be thinking that there's 20 terms, but if we do the number of terms, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 terms. So this time n would be 21. So we would say that our sum is 21 terms divided by 2. The first term, if we plug in 5, so a sub 5, is 4 times 5 minus 7, which is 20 minus 7. So the first term is 13. And the last term, a sub 25, is 4 times 25 minus 7, which is 100 minus 7, which is 93. So if I wanted to continue and find my sum in a different color here, that would really be 21 over 2 times 13 plus 93. And if you get this in your calculator, your sum would be 1,113. So when you're doing this, please just be careful that you are going from the first term to the last one. Make sure you're counting your number of terms correctly. Make sure here you do not plug in 5 and 25. Make sure you actually plug in the output values once you plug in the term numbers, because remember we've been focusing that n represents the term number and the numbers you plug in are the output values. Okay? So we will also be doing more examples like this in class. I think these two are a good representation, but please come to class prepared tomorrow with questions about this. And yeah, good luck practicing.